I think we're good to go. So thanks everybody for joining me, and thanks for your interest. I enjoy sharing mathematics, and so this is wonderful for me, and I do think it's important that our community continues its work. I know a lot of you are teaching in this form, and maybe some of you are mainly interested in seeing how this can go. But for whatever purposes, I'm glad you're here. So the thing I want to introduce, the tool I want to introduce, are called Thom Cochains, and really the idea is that cochains are generally transcendental, except maybe if you're doing some work in a finite simplicial complex, or you're doing de Rham theory, in which case they're sort of like a volume with a direction, so to speak. But really, you know, if you say you've got a cochain, what that means is you have to take any chain, and we can just look at the standard generating set, and you have to produce a number. And so there's a lot of chains. So that's a lot of numbers you have to produce, and it's hard to do so explicitly. So for me, this was almost a pedagogical problem, teaching algebraic topology and being able to draw chains as finite linear combination. So you can give example of chains just by drawing pictures like that. That's, well, if I want a linear combination, I can draw my favorite chains. But how do you draw a cochain? So what I like to do is define what's called a tome cochain. And it's going to define a number using sort of an intersection, or you could think of this as a toll. So if I've got a submanifold of a manifold, they don't have to be oriented if you want integers, but they do need to be co-oriented. Then what is the value of the tome cochain on a simplex? And what I want is that this is supposed to have codimension n. And well, you're going to just take the preimage of W and you're going to count it. That's some finite set. Of course, now we want some transversality here. As I said in the announcement, we were going to use differential topology a fair amount. And if this is, so if sigma is an embedding, this is equal to just the count of the image of sigma intersected with W, and again, with some transversality. So what's the first example, my favorite example? If M is R2, take away the origin. Let me scroll here a little bit. Then a good example of W doesn't need to be compact or anything. I can take the x-axis with positive x coordinate. So then the picture is like this. So M is just R2, which is the board, minus the origin. W is this positive x-axis. And then the value on some chain. So if I've got some sigma, which can do this, then I'm going to count these with signs. So maybe this is a plus here and a plus here. Or sorry, that would be a minus. And then a plus here, plus, and another plus. So sigma, so tau W on this sigma would be 2. So, so that's how they work. They just evaluate by intersection. And if you know some differential topology, I mean, first of all, this is not defined on all chains, because if I want to make such a count and have it be a finite number, then the chain couldn't have an image inside the x-axis in this case, for example. So what you need to do is you consider this tau is in a cochain group that's a quotient of the usual cochains, because it only evaluates on a subgroup of the usual cochains. And so that's fine. So these are defined just on a subgroup of chains. And then a little theorem. And again, this is something that now I should say, this is with Annabelle and Greg. This is a quasi-isomorphism. So you can use these Thom cochains to represent cohomology. The other key proposition or theorem that gets you going pretty fast is that the co-boundary of one of these things is, I'll let the audience ponder for a moment, what should this be? Nothing else but, oh, that's interesting. I've not seen AWW behave in that way before with so many arrows, but hopefully it will behave. The co-boundary of such a cochain is tau the boundary, and of course that implies that closed submanifolds represent cohomology. So this is a standard fact, but this is a more direct cochain approach to it. Two standard ways you may see this, again, in aforementioned de Rham cohomology, you can actually make a Thom cochain that's in de Rham theory by taking a tubular neighborhood and having a form that's sort of just normally supported and that integrates to one on any fiber. Or if you know Poincare duality, then what you can do is say, well, depending on what version, let's just talk about a closed manifold. Then a closed submanifold defines a homology class by Poincare duality that defines a cohomology class in a complementary dimension. And so, so that's how we associate cohomology to submanifolds. But this is more direct. I won't give the, let me give just the idea of proof, and we can call this an exercise. The idea of the proof is it's akin to the proof that the degree is well defined. And by degree, I mean in differential topology. And so it uses the classification of one manifolds. Sorry about that. And so, so this lets us again denote, represent a cohomology class by a submanifold. And you should really think of this as a chain, cochain version of, or underlying of Poincare duality. And we'll come back to this. In fact, towards the end, I think there's a number of other topics that are going to take priority, but towards the end, we'll share some progress on getting some mileage out of this idea to better understand the interplay between the smooth topology of a manifold and its homotopy theory. I mean, there's a lot of fun and games, by the way, you can think through now. For example, what is an induced map on cohomology? That'll just be taking pre-image, and you have to use the lovely basic fact from differential topology that the normal bundle of a pre-image is just pulled back from the normal bundle of your manifold, again under some transversality. Wrong way maps are images, and those again under some properness assumption, and those really can change dimension. So all of a sudden, the whole theory of wrong way maps becomes sort of more concrete rather than this sort of formal diagram chase. So, but we'll be developing and using these, and then a key. Let me just say one key that key first. Theorem or proposition is that, if I take the cut product, that's going to end up being, well, what you think of. But of course, that can't be true. This is like de Rham theory, but now I'm over the integers. And if this were true on its own, then cut product would be commutative, and there would be no Steenrod operations. And I don't know, we could all go home. We could get the universe to vanish in its illogic or something like that. But there's a term. And so this says that on cohomology, so cup product is intersection on cohomology. So we'll come back to those ideas in a few weeks. We can also discuss them a little bit more if folks are interested in office hours. I wasn't sure how seriously folks wanted to take this, whether it's more of a diversion or something they want to look closely at. And I could, once I get Anil and Greg's permission, maybe share a bit of what we have written up on this topic. But I wanted to give two applications. And they're of a different flavor. One is a sort of a conceptual approach to the cohomology of the space of loops in a manifold. So these are based maps from a circle into your manifold. Those are important spaces throughout geometry. And then the other is more substantive. In fact, part of why I say conceptual is I actually haven't worked out proofs for the theorems that you'd want to prove there. But I do think it's worth sharing as a point of understanding, and then also to understand, and this here we will apply it, the homology and cohomology of Euclidean configuration spaces. So so that's sort of what I wanted to do with them. Let's see. My apologies as I need to move. Feel free in the chat. I will monitor the chat in the Zoom. I think there might also exist a chat in the YouTube stream of this, but I won't be monitoring that. So let me know if things need to be larger, or if there's any serious thing that I'm missing or anything like that. I will try to monitor the chat. Although right now I'm not seeing, let's see. No, that's not what I wanted to do. That's not the right button. Sorry, let me, yes, okay, thank you. Let me answer some of the questions on the chat. I'm sorry for not, I thought I had it up, but I didn't. The first theorem holds for any W. Well, let me, let's look and see what I labeled as the first theorem. Yes, basically any W with boundary. And again, we can come back to these later. This is, in this catch up, it's kind of an advertisement. Let's see. Am I missing a sign? Sorry, I'm not sure what that refers to, but I could, let me just say in blanket, there are potentially some signs, that could be missing from various things. And what I'll generally do is try to write plus minus if there's a sign that I'm suppressing. And yeah, so then we're talking about cup product. That's true. Okay, I think that's what I want to say about things in the chat so far. Let's see, is there anything you can say of why I want to use cochains and tome forms instead of always working with chains and transversal intersections? Yeah, a little bit. I mean, part of this will come in the configuration spaces. My first answer here will be more philosophical than mathematical, namely that often if you've got an interesting space, the geometry of the that's sort of indigenous to homology and the geometry that's indigenous to cohomology aren't necessarily the same. So it's actually, it's important to allow for both to have fairly equal footing and look at the pairing between them. And so that's exactly what will happen with configuration spaces. So that's a great question from Manuel, and and hopefully that will come through in a few different cases. That will also be the case for Grassmannians, for Eilenberg-MacLean spaces, for symmetric groups. You'll see that somehow there's natural or native approaches to homology and cohomology which are distinct. And if you pay attention to both of them, that also allows you to pair them. And that can lead to some rich combinatorics. And again, so today is going to be an example of that. Okay. So let me tell you a little bit about loop spaces from this point of view, because this, so again, loops on M is the space of based maps from a circle into M. It's an infinite dimensional space. Morse had this amazing approach to it through through differential geometry. So these if you want to be more categorical, you could say, well, the spaces, if you're in the right points at category, are enriched over themselves, and this is so the collection of maps itself forms a space, and that lets us use the tools of topology to understand our Hom sets themselves. So in particular, you want to understand the homology and cohomology. And I'm going to focus on the cohomology. And for those of you who know, there's the answer. It's pretty, but it might feel like it's well, anyways, it's not the most immediate and intuitive, but I'm hoping you get some intuition from these Thom Cochains. So now let's suppose I've got a chain on the loop space, and I'm going to think of an n-1 chain, and then I'm going to define the Thom Cochain to W. So whereas before, its value, and I'm going to put bars around things, and that way I remember that I'm in the loop space. Its value on sigma is given by, well, I can really think of the adjoint of sigma, and that's a map from the product of the simplex with the interval which is parameterizing the circle to M. And I'm just going to look at, if I'm thinking of intersection again, I could think of the number of times that sigma adjoint intersects W, or the preimage under sigma adjoint, but I'm avoiding that for notational simplicity. And so the picture is, if we have our M, and then we have our W, and then sigma is some family that we can think about this sort of sweeping out. And then what I'm going to do is just count the number of times that that sigma sweeps out through W. So in this example, it's just 1. So that's what, this is what bar tau W is counting. Okay, so that's all well and good. Some people call this the suspension or desuspension of the cohomology class associated to W. And we can, again, we think of this as a number of times that sigma hits W, but sigma is now a family of loops. Number of times a family of loops hits W. And the next thing I want to say is we can count number of times we hit, say, some V, and then in the same loop, W. So let me formalize that a bit. So in order to do that, so what I want to do is, now I'm going to take a n-2 dimensional family of things, or I could really my apologies again. And I have to do this on my own board. And maybe I really want to think about this as an n1 plus n2 minus 2, where n1 and n2 are the codimensions of V and W. So if I have such a family, then what I can do is evaluate it at 2 points. And by that I mean, and this is sort of this generalization of the adjoint then, what we can do here is if I have some, say, S is just an element of the simplex, and I'm going to think of delta 2 as a T1 and T2, then I can take my family at the element of the sigma simplex, that's a loop, and evaluate it at T1, or evaluate it at T2. So I get 2 points. And what you can do is you define tau V bar tau W on such a sigma to be the count of the pre-image under this EV2 of V cross W. So really what that says is that, again, as I said informally, you're passing through V, and then at a later time on the same loop, you're passing through W. And so this is a way that now, given a list of submanifolds or cochains, you can make a cochain on the loop space. Now, I got a question. Back in this picture above, my drawing abilities are limited. So the way you want to interpret this picture is the red manifold is sort of coming out, and the yellow sheet only intersects it at one place. So it sort of goes over here and then under there, or vice versa, or something like that. So you're welcome. Okay, so well, let's think about some of the properties of these cochains. In particular, again, we like to have not just cochains, but cocycles, so that you can then take, so you want to think about the boundary. And as you might expect, the co-boundary of the first kind of cochain is given by the tome class of the boundary. And the way I want to say this informally, and this discussion is going to get more and more informal here, is that if W has boundary, and I had this family, which now will be, maybe I'll draw it in a different color. Now imagine a one parameter family of those families, where I've got these intersection points. They can sort of run off the boundary. Really what you want to do is just look at this definition by adjointness. And again, there's a little Stokes theorem classification of one manifolds that can establish this for you. But again, this will be a briefer treatment of some of these things in a catch-up lecture. But here's the real fun. Now let's think about the co-boundary of, if I have a V and a W, and you think about the ways that through you think about the ways that through a one parameter family, you get you can sort of change your count or run off the boundary. And that's exactly what you're going to be thinking about when you think about the co-boundary of bar tau V, bar tau W. So again, you can run off the boundary of V. So here's where I'll you can run off the boundary of W. But there's something else that can happen. Namely, so that's running off the boundary of W. Namely, this has an order. And so if I have a one parameter family that goes through V and W, well, if I hit the intersection, then that count of hitting V and then hitting W, again, look back at the definition of the cochain, and you see that it's ordered here because I have V cross W that I'm considering. But if I'm in their intersection of V and W, then that ordering could change well, first it's sort of a double point, and then as I go through the family, the ordering could change. And so you get a term like that, again, assuming some transversality. So there's a question, why these bars? Does this have anything to do with the usual models for cochains on a loop space? And so let me actually just introduce a little bit of terminology, and this is also going to be play an even bigger role in the usual noon lecture. So definition, I'm just going to call it bar A. This is going to be the, for those who know, the Hochschild chains with trivial coefficients, but this definition I'm giving for people who don't know. You're just going to take what looks like the tensor algebra. Technically, we want to think about it as the cotensor coalgebra, but the funny game is that you write these instead of as tensors, you write them as bars. You write your tensors as bars, and you put a couple out at the ends. And what you have is then, and so let A actually have a differential as well. So a differential graded associative algebra. If you have just a regular algebra, you could just put a zero differential on it. And then what D of such a thing is, comes in two pieces. Let me come over to the right for a little bit. So first of all, you use the Leibniz rule. So you're going to take your dA1 bar, A2 bar, etc., and A1 bar, dA2 bar, etc. So you just extend the differential to the tensor algebra, really cotensor coalgebra, by the Leibniz rule. And then what you do is you sort of let the algebra elements out of their cages, and they do what algebra elements do, which is multiply one another. And again, I'm suppressing lots of signs. So this is just something that anyone who knows what a differential graded algebra could follow this definition. And then in topology, this arose because it had something to do with loop spaces. Namely, so I'm stating this in cohomology. This is really due to Adams-Hilton. Some people like to say this leads to the Eilenberg-Moore spectral sequence, but I think of it as the Adams-Hilton, and I'm stating it in cohomology, so maybe I'll just say it's equivalent to the Adams-Hilton theorem. Namely, that if I want the cochains on the loop space, there's a quasi-isomorphism. They were working in homology. The arrow went the other way, so naturally the arrow goes this way, to the bar construction on the cochains of the space. And let me state it as a conjecture. So what I was just telling you about these intersections, and I haven't written these down, and there's some serious technical issues that I'll mention in a second. There's a map going the other way. Which sends tau v1 bar, tau v2 bar, to, well, tau v1 bar, tau v2, I had defined this as a cochain. Oh, let me move up the window. So, and so this side is the sort of formal and this side is the geometric that I just gave you. So anyways, this is a way to understand why a bar construction arises when one is studying loop spaces. And I'll carry this further for those who like these kinds of things. When we talk about classifying spaces and loop spaces, there's more kinds of bar and cobar, and I like to say that this area is about loop de-loop. And yes, this is for simply connected. And Manuel knows very well the generalization because he's worked on this, and I'll also say something about the non-simply connected setting in the lecture next week. Not this exactly, but the quote unquote abelian version of this, derived abelianization or something you might want to say. Okay, I think that's what I want to say. So this is one way that Thom Cochains can sort of point you to some interesting both geometric and then sort of combinatorial and algebraic structures that you can understand now in terms of intersections. Let me move to the second application, and this will be a real application, not just philosophy and conjecture, if you want to call what we just did that. And that's to looking at configurations of endpoints in RD. So what is this? This is really, it's the Cartesian product but I'm going to take away points where some points are repeated, are equal. Okay, so it's a fun space because it's locally, it is a subspace of Euclidean space, and you can just think about points and they're labeled, so you can say x1, x2, x3, or you can just say 1, 2, 3. I often will. And so what I want to talk about is the homology and cohomology. And again, I like to find sort of native representatives for such, and then play with them together. So for homology, let me just say that let me just go ahead and give the definition, because I want to do this for about 10 minutes. So given a tree, or more generally a forest, with leaves labeled 1 ... in, we're going to define a submanifold without boundary. So it's the kind of thing that can define homology. And let me give an example first. And that submanifold is going to be homeomorphic to a product of d-1 spheres. And so we're going to take its fundamental class to get a homology class. So let's give an example. If my tree, let's do this. I'll make it a forest right away. 1, 2, 3, 4, 5, 6. So to such a picture, to such combinatorial data, I'm going to make a torus. This won't be canonically defined, but the ultimate homology class will be canonically defined. And what I have to do is, well, there's 3 connected components to the forest, so I'm going to specify sort of 3 sort of absolute center points. And then about each of those, so the simplest one is 4 here. There's no trivalent vertex. So by a forest, I mean a unitrivalent graph. The roots, by the way, are all sort of fixed to, say, the x-axis, and they're upper half planar. And so here in 4, there's no associated point. So in the configurations that we make, we're always going to see 4 on its own. Whereas for 2 and 5, what we're going to do is we're going to think of this as the center of mass for a small sphere. This is in, again, dimension d, so this will be a d-1 sphere. And 2 and 5 will be orbiting each other. So this is parameterized by an SD-1. Oops. Okay, and then the third one is the most interesting. This is, again, a center of mass. I should have drawn these a little bit further apart, but you can then take the internal vertex that's lowest, and I'm going to think about it now separating, well, there's point 3 is one offshoot of that lowest internal vertex. But then I'm going to write the center of mass of points 1 and 6. So here I have an SD-1 cross SD-1 worth of possibilities. So this is a submanifold. There's a question, is this the Fulton-McPherson compactification? No, this you don't need to compactify because this is just a subspace of the configuration space. But if I let the radii of these, quote unquote, go to 0, and I take the limits of these, in fact, I do get strata in the Fulton-McPherson compactification. So for experts out there, when we talk about this homology, we're going to find that all of these homology classes are represented by strata. The way I say it is that the Fulton-McPherson compactification wears its homology on its sleeve. It's these sort of little submanifolds out on the boundary that, and they're really inside the boundary. They're deeper and deeper strata, but they're all out, quote unquote, out there on the boundary. But we don't need the compactification. This is just a submanifold. So again, that's how we get some homology. Now the data for cohomology is going to look different. So again, this up here was homology. Cohomology, I'm gonna, I guess I'll draw it compatibly. So I need a graph which is going to be the union of some acyclic things. And I also, by the way, I think it'll be most convenient to, if I want, I can choose one vector once and for all, but I will label these by little vectors in my Euclidean space. And so in the cohomology picture, this is going to be a submanifold. And then I'm going to take the appropriate tome class. And what submanifold is it? Well, this graph will just say that and these are, say, u, v, w are unit vectors, and it would say that x6 minus x1 over its norm equals v, and I also want x3 minus x1 over its norm equals w, and then I would also want x5 minus x2 over its norm to equal u. And that's a perfectly well-defined submanifold. It's a proper submanifold. It's not something nice and compact like the torus, but it's very much analogous to, in fact, the positive x-axis. You want to think of these as, if these are complements of some union of hyperplanes, then these are some linear spaces kind of going out orthogonal to these hyperplanes, if you will, or not orthogonal, they're going out sort of in these directions, v, w, and u. And so, now we can take their tome classes. And so let me recap now to a tree or forest. T or F, we get some homology class in the configuration space. And to a graph, G, we get some cohomology class, I'll just call it tau G, in the cohomology of the configuration space. And here's the fun exercise, so to speak, but I think I'll spoil a little bit of the fun because it brings me to a point that I was making before. So, question: what is the value of this cohomology class on this homology class? Let's just look at one little example. Say G is, let me just have only 3 and connected graphs and forests. I hope folks are hearing me okay. So we have, we're asking, and let's maybe, let me put this one is the vector going up, the unit vector going up, and this one's the unit vector going to the right. So that's my U and V. So, well, the whole point of tome classes is we can calculate by intersection, right? Yes, the edges of G are oriented. Thank you, I should have said that. I'll write that back up here. And by the way, this is in a few different papers of mine, again, because we'll run, time's gonna end and we'll switch Zooms actually. Sorry, you'll have to quit out of this one and go to the next one. But this is in a paper called the non-equivariant, I put it in parentheses and I forget, but homology of the little disks operad. So this is a part of a wider story. I sent this link out. So see that paper of mine on the archive. It's, again, there's a few new ideas there, but it's mostly expository. So, but let's get back to how would we calculate this intersection. So if I have F is the submanifold where where let's just think in the plane, I've got an orbital system where points 1 and 2 are orbiting each other, and then point 3 is orbiting antipodal to their center of mass. And what I want to do is have 1 to the right of 3, whereas it's under 2. So do I ever have, can I arrange 1 to be the right of 3 and under 2? And you can see that, yes, this happens exactly once. It happens if, well, so 1 under 2 means that this, this thing here, I would have to have, so I have that as a parameter, so I can choose the parameter with 1 under 2. Then it's going to get a little bit tricky to have 1 to the left of 3. They're going to maybe have to be, the centers of mass are going to have to be offset a little bit. But anyways, let's see. But in fact, that does also happen exactly once. So the center of mass is offset a little bit so that this is antipodal to that, and then 1 is to the right of 3. So this becomes a, sorry, let me go down to the given. So the intersection becomes, well, just seeing whether any point in this family satisfies those conditions. It's just the intersection of two submanifolds. And ultimately, the fun thing is, let me give you the final answer. So the answer is take for every edge of G, look in the tree at the minimum, or the greatest, sorry, it'll be the maximum, my apologies. Let me just say one thing and get the picture in front of us. So I'm going to look at the greatest vertex under both. And I'll just do an example. So here's G, 1, 2, 3, 4. And I'll do a tree, say 1, 2, 3, 4. So for every edge, like from 1 to 2 here, I'm going to think about under 1 and 2, here's the greatest vertex. And then I do the same thing for every edge. So I'll use color 1 to 3. Here's the greatest vertex. And then finally 3 to 4. Here's the greatest vertex. So this gives you a map from, just as sets, the edges of G goes to the trivalent vertices of T. And this homology-cohomology pairing ends up being plus or minus 1, and it's a very simple sign, but it does depend on the ambient dimension, D, if this is a bijection and 0 otherwise. So purely combinatorics, and I will scroll up momentarily. Purely combinatorics tells you about the pairing of homology and cohomology here. So this is why I like to have sort of a more quote unquote native approach to cohomology, because it's one thing to sort of have a vector space and another thing even to have a vector space with a basis. And it's another thing altogether to have a vector space with a basis and its dual with a co-basis. And so treating cohomology in this way allows for this. And so the configuration spaces, as we'll see in the momentarily, I'm going to switch over to the other Zoom and stop recording here. They give rise to this lovely approach to both Lie algebras and coalgebras that was found by people like Reutenauer, although not as fully developed as we did. But we only found that approach to Lie coalgebras by letting cohomology tell its own story. So I'm going to stop there and hopefully see a lot of you over in the other meeting.